Let's look at number 2 from worksheet 13. In this question we have a solenoid. This is the side view of the solenoid and this is the end view, okay, looking from this side or this side. So there is some current flowing through this solenoid, and as a result, because we know that the magnetic field of the solenoid is given by mu naught Ni over L. So since there is current in this solenoid, that means there must also be magnetic field in the solenoid. So there is this magnetic field in the solenoid, and the direction of the magnetic field is given by right hand rule. So you point your thumb towards the direction of the current. In this case the direction is clockwise, and imagine that you are wrapping your fingers around this wire, pointing your thumb in this direction. When you do that, inside the solenoid your fingers would be pointing into the screen, okay, and that would be the direction of the magnetic field. So that's the direction of the magnetic field. Okay, that's the direction of the magnetic field. So magnetic field is pointing into the screen. Okay. Now it says that this current is decreasing, so this is decreasing. That means our magnetic field is also decreasing, or we can say that this magnetic field is changing. That means the flux or the magnetic field lines going through this surface or this face of the solenoid is also changing. So that results in the change in flux. And from the Faraday's law, if the flux is changing, there is EMF induced, that is given by N delta phi over delta T, and if there is E, then there is also I induced. Okay. So to induce I, we need a coil or some kind of wire, but we are finding the electric field at 1 and 2, and we don't have any wire at point 1 and 2. Okay. But the idea here is, if you were to have a coil or a wire at point 1 and 2, okay, something like this, then there would be current flowing in this wire, okay, because of the induced EMF. Now, what causes the current to flow in the wire? That's the main question. Okay. So flow of current means there is already charge in the wire, so a force needs to push the charge, okay, so that the charge flows in the wire. So what pushes the charge in the wire is the electric field. Okay. So this current is actually due to the electric field produced in the wire. Even when there is no wire, there is electric field produced. Okay. And the main idea here is, when there is change in magnetic field, it produces electric field around it. Okay. And to find the direction of the electric field, we can just find the direction of the current, because the current is being pushed by this electric field along the direction in which the current is flowing. If the current is flowing like this, that means the electric field is pushing the charge or electrons in this direction, or the charge carriers in this direction. If the current is flowing in this direction, that means the electric field is pushing the charge carriers in this direction. Okay. So if we could find the direction of the current, then we can find the direction of electric field. Okay. So we can assume that there is a wire, okay, going through points 1 and 2, and there is current flowing in that wire. So now we can use Lenz's law to find the current in the wire. So if you remember the Lenz's law, so what Lenz's law tells us, so recall that. So that's some imaginary wire. Okay. So Lenz's law tells us that when there is decrease in flux or decrease in magnetic field, whenever there is decrease in magnetic field, that decreases the flux. So when there is decrease in flux or magnetic field, there would be an induced magnetic field. So there would be induced magnetic field in the same direction as the original magnetic field. That will compensate the decrease. You have a magnetic field in this way, and if the magnetic field is decreasing, okay, it's going down, that means in order to compensate this decrease, you will need this additional magnetic field, okay, and that additional magnetic field is B induced. Okay. And that's the Lenz's law. Lenz's law is, again, wherever there is change in magnetic field or whenever there is decrease in magnetic field, you will have some induced magnetic field that will compensate that decrease. So this magnetic field is decreasing. Now in order to keep it from decreasing, going to 0, you need this additional magnetic field in the same direction, okay, just to compensate that decrease. So this red one is B induced, and the current produced is the induced current, and that induced current actually is associated with this induced magnetic field. Okay. So find the induced current by using the right hand rule. Point your fingers towards this induced magnetic field, and then wrap your hand around the wire, or imagine that you're holding this red loop. So when you do that, your thumb would be pointing in clockwise direction, okay, in this direction. So point your fingers into the screen and then hold the loop. Your thumb would be pointing that direction, so it's clockwise. Okay, and this current, imaginary current, is due to the electric field. This change in the magnetic field is producing producing an electric field around it, okay, and that electric field is what is causing the current. That means the electric field at this point would be tangent to this curve, okay, so that would be the electric field, and it's pointing along the same direction as the current, so it's pointing that way. And at this point the current is going down, so electric field would be pointing down, because this is the electric field that is causing the current in this wire, okay, so that's the electric field at that point, and that's the electric field at that point. So that means at point 1 the electric field is pointing down, and at point 2 the electric field is pointing to the left.